We're going to review chapter 8 for exam 6. And that will be this Thursday. Yes. We'll have this exam on Thursday. And I'm working from our review document. And the only one I gave you guys this time was version 1. I'm pretty sure. Yeah, version 1. All right, so let's see how many we can get through here before we have to go in the lab and finish up. Amanda Combs said it was okay, so everything that we did last week is still on the board. We didn't have to erase anything. All right, move on. The force between two bodies having identical electric charges is, well, let's think about it. Right? What kind of force does that one experience with that one? It's repulsive, right? Or that one with that one, it's also repulsive. The only one where you get electrostatic attraction is where the charges are opposite. So which one fits that? Force of repulsion, A. Right. That was easy enough. It's going to be stubborn today. Atoms having equal or nearly equal electronegativities are expected to form what type of bonds? Right. What type of bonds do we have available? Now we have ionic bonds. We have covalent bonds. And we can have polar covalent bonds or nonpolar covalent bonds. So where would those two fit? If they have nearly identical electronegativities, well, they're definitely covalent, right? If they're going to bond. And their electronegativities are so close to each other, they should be nonpolar. Right? So that would be C, nonpolar covalent bonds. Let's get number 3 and 4 together. Right. For the elements, cesium, fluorine, and chlorine. The order of increasing electronegativity. Cesium, fluorine, and chlorine, right? Okay, so what's the trend? Remember the trend? Periodic table. And go down here like this, and this, and then we have hydrogen here and helium here. Okay, increasing electronegativity is lower left to upper right, which means from left to right in a period is increasing, and from bottom to top is increasing. So where are these guys positioned in the periodic table? Well, this one's going to be the greatest. Fluorine, obviously. Fluorine, nothing has a higher electronegativity than fluorine. So it's got to be over in order of increasing, right? So this one's greater than anything below it, right? Where's cesium? Cesium's the lower left-hand corner, right? So it's going to be the least. And that means chlorine's in the middle. So cesium, chlorine, fluorine is the correct order. About 4. The electron pair in carbon-fluorine bond could be considered. Let's see, what are our choices? Closer to carbon, closer to fluorine. And because, okay, so we say what it is and why it is. And so when we've got this bond, okay, where are they positioned relative to one another in the periodic table? Of course, fluorine's far right, carbon is 3 steps to the left. Okay. So we're going to have a polar bond in that direction. Okay, which one fits that? Closer to fluorine, right? B. Well, that's it. Right. Let's see if the because is correct. Because fluorine has a higher electronegativity than carbon. Okay, that's it. That's the only one that makes sense out of that bunch. About 5. Which of the following molecules has no dipole moment? All right. How do we know whether a molecule has a dipole moment, whether it is polar or not? Remember the 2 bits of information you need. I'm sorry? No, well, not necessarily. The 2 things we talked about in class, and should be in your book also, is it must have polar bonds. That's the first checkbox. If there is no polar bonds in the molecule, it can't be polar. But even if it has polar bonds, you have to consider the geometry of the molecule. Right? If the geometry is such that the polar bonds cancel one another out, then you have a nonpolar molecule. So let's see, what are our options here? Carbon dioxide. That's A, B, C, and D. Oops. A is D is all, and E is none. Okay. So which of the following molecules has no dipole moment? All right, so we're going carbon dioxide, ammonia, and water. We've drawn water before, right? Oxygen, hydrogen. Let's see. I have to refresh my memory. Yeah. Okay. So if we drew the Lewis dot structure for water, it would have 2 lone pairs here. It would have hydrogen down here, which means those bonds are polar. Plus you've got these 2 pairs up here, a negative. Right. So that would be the polarity for water. How about ammonia? If we look at ammonia's structure, it has a hydrogen back here, hydrogen here, and forms that triangular base. It also has a lone pair up here. Nitrogen is more electronegative than hydrogen, so it's going to have these 3 like that, like that, like that. And its polarity is going to be like that. Right. So it's polar. Right. That's polar. That's polar. How about carbon dioxide? We drew carbon dioxide in class. Right, there you go. So you got polar bond this way, polar bond that way, equal in magnitude, opposite directions. This one is non-polar. Okay. So we had 3 molecules with polar bonds. The only one that was non-polar was the linear one, because those dipole moments cancel one another out. All right, that was 5. 6 and 7. Which of the following has the smallest radius? 6. B, C, D, and E. Okay, so we have argon here, we have sulfur, we have rubidium, we have chlorine, and we have potassium. Okay. Okay. The smallest radius. We've got a pretty good idea of atomic radii. Right? We know that the radius from left to right decreases, and from bottom to top it decreases. So for atomic radius, this is decreasing. Decrease from lower left to upper right. or from upper right to lower left, increasing. All right. So which one would have the smallest radius? Well, the smallest radius for the atom, for the neutral atom, would be up here. Right? We don't have one of those. Maybe chlorine's the closest we can get. If it were atomic. Okay. The problem is these guys are ions. So when you add an ion, when you add a negative to this chlorine, it goes from this to that. Makes it bigger. When we lose an electron from potassium, which is just beyond, right? These two are isoelectronic with argon. Argon, chlorine, potassium. They're isoelectronic. How about sulfur? Sulfur is isoelectronic. Let's look at it that way. Okay. So what would their electronic configuration be? It'd be the same as argon. Right? Argon 18. That's going to be 1s2, 2s2, 2p6. I haven't looked at my work problems to see if I did it this way or not. I'm just off the cuff here. 3s2, 3p6. How many is that? 2, 4, 10, 18. That's it. So that's argon. That's also the electronic configuration for each one of these. So if they've got the same number of electrons, which one has the most number of protons? Right. Argon's 18. Sulfur is 16. Right. I'm skipping rubidium for now. Chlorine has 17. And potassium has 19. So of these four, which one would be the smallest? It would be the one with the same electronic configuration, but the highest nuclear charge. The highest number of protons would drag those electrons in. So out of those four, this would be the smallest. Now let's look at rubidium and see where it fits in all this. Rubidium is below potassium in the chart. Right. So as we go down, they've got the same charge. So this one's going to be bigger than potassium. So I think potassium should be the smallest ion of this group. Does everybody see how I got that? Okay. All right. 7. Which of the following arrangements is in order of decreasing size? All right, let's see if we got the right decreasing size. All right, all the carets are left pointing to the right. Okay. Decreasing size. You know, I should have left that other thing up there. Now, do I have to redraw it? Let's see. We've got, we do have gallium. Gallium 3+, which has 31 protons. Then we have calcium 2+, which has 20. Yep, okay. Then we have potassium plus, which has 19. Then we have chlorine minus, which has 17. And we have sulfur 2-, which has 16. What else do we have? Sulfur, chlorine, potassium, gallium. Okay. I think that's all of them. All right. We've already determined that this one and this one are isoelectronic. How about calcium? Yeah. Calcium is isoelectronic also. It's got the same configuration as argon. Okay. So these are isoelectronic with argon. Okay. Where does gallium fit? Well, gallium is to the right of calcium. right? So even as an atom, it's going to be smaller, right? Left to right, gallium is going to be smaller than calcium. And also we're removing electrons. We've removed 3 electrons from this one too. So I think gallium is probably the smallest one. So I would put gallium 3+ over here. And then we would go to our isoelectronic series and look at the nuclear charge. Then we've had calcium. Then we'd have potassium. Then we'd have chlorine. And then we have sulfur. Now, is that according to B, that's what it should be. I mean, and it seems logical to me. Let me see, what's in 8? Okay, I'm going to sneak another one in on me. All right, number 8. In a reaction between, let's see, yeah. In the reaction between magnesium and sulfur, magnesium and sulfur, magnesium atoms what? Become anions, become cations, become part of polyatomic, share electrons with sulfur crystalline. All right. We've got a metal and a non-metal that are very far apart in the periodic table. And you can bet that this one, all metals like to become cations. And anions and non-metals like to become anions. So this one's going to become 2+, and this one's going to become 2-. So the magnesium becomes a cation, like B. And this is going to be an ionic compound. Number 9. Choose the molecule with the strongest bond. All right. So let's see. We've got A, B, C, and D. And one that says all are equal. All right. They're not all equal. You can throw that one out. So we've got this F and F. We've got the chlorine and chlorine. We've got the bromine and bromine. And then we got iodine. And there we go. So which one has the strongest bond? Okay, they're all single bonds. So we can't use a comparison of single, double, triple bonds. We have to look at the atoms that are bound together. So what we're looking at is a sharing of electrons. And these are huge atoms. These are a little smaller, these are a little smaller, these are smaller still. And they got of course, they're going to be nonpolar, each one of them. Let's see how I approach this. Just to save time. I don't want to be dancing all over the place. So what we're looking at is how much orbital overlap can we get from these two? From these two, or these two, or these two, or these two. If we drew the Lewis dot structure, right? We have this bond here, and these had right like that. But which orbitals overlap? Well, the orbitals that are available, that's going blank. The valence orbitals that are available are p orbitals for each one of these. Right? Because they have p5 and we need one more. Right? So each one has this on their outer shell. Well, what you got here is with these big atoms and their 5p orbitals, the overlap is going to be less. The overlap is going to be less for this one, and the overlap is going to be greater for this one. So when we look at orbital overlap, we get this increasing p orbital overlap. Okay. So logic would have it that as we move up, the bond would get stronger because the nuclei get closer together and we can overlap the orbitals more completely. Except we've still got the positive and negative charges to deal with. So as you get closer and closer here, you find that the fluorine nuclei, each one has 9 protons and 9 electrons. And you can't get close enough to overlap more than the chlorine did. So even though the chlorine atoms have 17 each protons, those protons are farther away. So the overlap here is maximized. And here, we can't get close enough because of these, because the atoms are smaller and the positive charges, the nuclear charges repel one another along with the electrons. And there's not enough shielding. Right? Remember what we talked about shielding. When you move down in a group, you get those core electrons that are shielding the nuclear charge. So as the shielding is removed from here to here, the effective nuclear charge increases dramatically for a fluorine and fluorine. That's why the strongest bond is there. Okay. Right, we look at it this way, overlap, right? Overlap closer, 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 except too close. And we start getting repulsion. So the strongest bond out of this whole group is the dichlorium. All right. Let's see, Heather. Oh, okay. Nobody new showed up. How about number 12? These molecules have a 0 net dipole moment. Just a second. Check something. Okay. These molecules have a 0 net dipole moment. All right. They must be referring to, yes, the ones above. Okay, so we've got, let's put them over here. Roman numeral 1, 2, 3, 4. We have a 5. Yeah, we have a 3. Okay. So we got this one, boron trihydride, nitrogen dioxide, sulfur hexafluoride, ozone, and ECl5. Okay. What we have to do here is draw their Lewis structures in order to determine if they have a net dipole. Net dipole because, well, 0 net dipole. All right, what you're going to find is well, we did this. This one was deficient. Remember that one? It's deficient in its like this, like this, like this, like that. Right? It's trigonal planar. And even though I'm not sure how far apart they are, but even if they did have a dipole for the bonds, they would cancel each other out. So this one is a net zero dipole moment. We know that. How about NO2? NO2. So 5 valence electrons here, and 6 times 2 here would be 12, 17 electrons. So we do like that. That's 2, 4 minus 4, 13 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right. So in this case, we have 3 groups, and it's going to be trigonal planar electronic, but like that. It's going to be bent molecular. So we have a net dipole in that direction. So it can't be 2. 2 can't be. That's a polar molecule. How about SF6? That was before, I think. What we have to do here is decide, are there any lone pairs? If there are no lone pairs, then we know what this structure is. So if we have SF6, then 6 times 7 is 42. Right? And sulfur is the same as oxygen, it's 6. So we have 48. So S 1, 2, 3, 4, 5, 6. Like that, like that, like that. Okay. I'm drawing the Lewis dot structure. 2, 4, 6, 8, 10, 12. That's 6, 36. 1, 2, 3, 4, 5, 6. 6 times 6 is 36. So that uses all of them up. All the fluorines have an octet, and we have no lone pairs. So the geometry of that molecule is octahedral. And all of the polar bonds facing toward fluorine cancel one another out. Okay? This is nonpolar. That's our second nonpolar. How about ozone? Ozone is a little trickier. Right? We've got 3 times 6 is 18 electrons. And so we do O, O, and O. 2, 4 minus 4, that's 14. 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, so we have 2 more to go here. All right, so this molecule is going to be like that, that, that. Actually, yeah, that's okay. Yeah, those there, those there, those there, oxygen here, and oxygen here. This is trigonal planar. Except, what is it molecular? It's bent. Now, this is one of those odd cases where I'm going to have to contradict myself. I said if all the bonds are nonpolar, then you don't have a polar molecule, but in this case, you do. And the reason you have a polar molecule is not because of the bonds, but because of that lone pair. Right? It's bent. These are nonpolar bonds, but you've got this big negative up here that makes the molecule polar. Okay. So, not that one. How about PCl5? And for every rule, there's always an exception. PCl5. So 5 times 7 is 35. And phosphorus is 5. It's in the same group as nitrogen. So that's 40. We have 40 electrons. So we're going to put these. Chlorine, 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 chlorine. 2, 4, 6, 8, 10. That means 30. And so we have 2, 4, 6. If we put 6 electrons around each chlorine, it'll make an octet. So 5 times 6 is 30. Right? They're all gone. That's a regular shape, and it's going to be what? Trigonal bipyramid. And since we have no lone pairs and the bonds are polar, but they're polar in such a way that they cancel each other out, this one is also nonpolar. So 1, 3, and 5 are the nonpolar molecules out of that group. Now, it took a lot of work to get that answer, but such as it is. All right. And we got 13. How many electrons must be shown as bonding or non-bonding electrons in the Lewis structure whose skeleton is this? This is an organic molecule. It's 4 carbons. It has an oxygen here. It has a hydrogen, 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 and hydrogen. Right. 1, 2, 3, 4, 5, 6. Wait a minute. Oop. Here we go. 1, 2, 3, 4, 5. 2, 3, 4, 5, 6. That one does need 1. Okay. So we got hydrogens up here. That, like that, like that. So what it's asking us to do for the Lewis dot structure is just say, how many electrons, how many valence electrons do we have? Right? That's simple calculation. We got 1, 2, 3, 4 carbons, 4 electrons each. We got 1, 2, 3, 4, 5, 6 hydrogens, 1 electron each, and 1 oxygen, which has 6. Right? So that's 16, 6, and 6. Right, 12, 28, right? 28 electrons. Okay. That was the easy one. Now we're going to need that. No, not the ones that I've identified. So in the interest of time, we're going to move on. (16) In the Lewis structure for ICl2 minus, how many lone pairs of electrons are around the central iodine atom? So even there they tell you the central atom is iodine, right? So you don't even have to think about that one. All right, so we're going to have 1, 2, 3 halogens with 7 electrons each is 21 plus 1, 22 electrons. Okay. We're going to have a central iodine and chlorines, right? So that's minus 4, 18, right? 2, 4, 6, 8, 10, 12, minus 12, 6 more electrons. They have to go on the central. So iodine is going to exceed the octet, 2, 4, 6. Okay. Now to answer that question, how many lone pairs? Pairs, lone pairs, not how many electrons, but how many lone pairs? 1, 2, 3. 3 lone pairs. All right. That was 16, 19, and 20. How many resonance structures can be drawn for ozone? Okay, O3. We did the O3 before. We can O. You know what? Hold on a second. Okay. 1, 2, 3. 3 times 6 is 18. 18. So that's 2, 4. Minus 4, 14. 2, 4, 6, 8, 10, 12. Minus 12. Okay, so we have 2. And that goes here. Okay. Right. 3 times 6 is 18. 2, 4, 6, 8, 10, 12. 2, 4, 14, minus 12, 2. Okay. Oh, okay. This oxygen, I drew it wrong before, right? I drew it wrong as if oxygen didn't have an octet. What we need to do is we can't move any of these over here and make a double bond to give it an octet. So we have to move this one either over here or over here. So that gives us two possibilities, right? We can either have this one or this one without the electrons. And these would be resonance structures. So we can have two resonance structures for ozone. Right. Which of the following types of molecules always has a dipole moment? Well, let's see. What are our choices? A, B, C, D, E. Linear molecules with two identical bonds. They will not have a dipole moment. They will not always have a dipole moment because for a linear molecule, if A and B are identical, then obviously there's no dipole moment. But if we can have a linear molecule like that also, if these are identical, there's no dipole moment. But if these are different, right, you could have a dipole moment, right? So always has a dipole moment, doesn't work for A. How about B? Tetrahedral molecules, 4 identical bonds, equally spaced. Right. This one never has a dipole moment. Tetrahedral molecule with 4 identical bonds. If the bonds are equal, then we're saying that if we have something in the center, and then we have this one, this one, this one, and this one, those would have to be identical bonds. Right? So even if they were polar, they would cancel one another out. So that one cannot always be dipolar. How about trigonal pyramid with 3 identical bonds? Okay, trigonal pyramid. And so we've got this triangular base, a trigonal pyramid. Okay, how do you get a trigonal pyramid? Use ammonia as a good example. Ammonia has hydrogen back here, hydrogen here, that, and then you have the base, the triangular base. And then you have a lone pair up there. That's a tetrahedron electronically. But if we cover this one up, we get a trigonal pyramid. The only way you can get a trigonal pyramid is a tetrahedron electronic structure with 1 lone pair. And that gives us, even if all these bonds are identical, that gives us that negative up here. So this one will always be dipole moment, bipolar. Trigonal planars, no. Trigonal planars are like this, right? You have an A in the middle and B here, B here, B here, right? So they're non-polar. Oh, they could be polar too, depending if this is something different. None has a dipole moment. This one, C, always has a dipole moment. I think that's the purpose of this question. It gets you to think about how did we arrive at a trigonal pyramid? You have to go through the electronic geometry first. And then if it has 1 lone pair at the top, then you'll always get a polar molecule. And ammonia is polar. All right, 21. Which set contains atoms listed in order of increasing electronegativity? Yeah, right. increasing. Let's see which ones we have. Fluorine, nitrogen, carbon, silicon. Fluorine, nitrogen, carbon, silicon. And the second one has phosphorus and oxygen added on, right? Then we have nitrogen, oxygen, chlorine. Chlorine's added in there. And then silicon, sulfur's added in there. Oxygen's already there, fluorine's already there. Then fluorine, chlorine, oxygen, sulfur. So these are all the atoms. All right. Which one is the most electronegative? This one right here. That's the most electronegative out of all of those. Can we find which one's the least electronegative? Right. Well, sulfur's down below it. Silicon's down below that. Silicon's to the left of sulfur. Phosphorus is more electronegative than silicon. Carbon's at the top, nitrogen's at the top, chlorine's to the right. So I think silicon out of this group, right? Silicon would be the least. Right? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. This would be the least electronegative, silicon. Okay, now we can fill in the differences in the middle. All right, which one's closest to fluorine? Well, it's a toss-up, really. I think oxygen should be next. It's right next door to fluorine, and it has the same. It has one less proton, but this one has ballooned up. Right, it has some more core electrons that are shielding it. So I think this one ought to be the next one. And then actually nitrogen. It's a toss-up. It's either nitrogen or chlorine. Nitrogen. Let's say it's nitrogen. And then carbon. And then chlorine 4, 5, 6. Oops. Sorry. 6. And 7. All right. Let's see, fluorine and nitrogen. No. Increasing electronegativity. A can't be it. Which one has fluorine on the right? B, C, or D, right? So we've got B, C, or D are possibilities. Okay. How about B? Oxygen, we said, is number 2. Okay. Nitrogen would be next. And then phosphorus would be next. Okay, B looks good. I guess we found our answer, didn't we? Yeah, we found our answer. It's B. Right. In the interest of time and taking a test, when you find your answer, mark it and move on. 22. Which choice has the bonds listed in increasing bond energy? Okay. Well, we know that probably for A, we're in a situation there where we've got hydrogen bonded to each one. We would expect hydrogen and fluorine to be the strongest, HF. Right? We don't have that FF problem that we described earlier. Hydrogen can get really close. It's only got 1 proton. So that one's in reverse order. It can't be. How about B? Single bond carbon, let's see, is less than double bond carbon. Yeah, is less than triple bond carbon. That's a good one. Yep. They're not all the same, right? So, and C, just to recall that one we did earlier, C should be chlorine is the strongest, then fluorine, and then bromine. All right, so that one, this is the way it should be. That's the way it shouldn't be. Right, so we found our answer. B. Triple bonds are stronger than doubles and doubles are stronger than singles. And since we have the same atoms bound to one another, all we have to compare is that single, double, triple nature. How about 23? I'm going to run out of time on it. In the gas phase, which of the following diatomic molecules would be the most polar? The most polar is the one where the atoms are furthest apart in the periodic table. But, all right, it's kind of misleading. Because cesium and fluorine should be an ionic compound. Oh, in the gas phase. Okay, that's the trick. Right? If we let them become a solid phase, then we do get those individual ions. But when they're in the gas phase, they're bound to one another as individual molecules. Okay, so the furthest apart is cesium and fluorine. That would be A. Cesium's way down there on the lower left, fluorine's upper right. That's the kicker. That one word, 2 words, gas phase, gaseous phase. That means that we can consider them as individual molecules. All right, 25. Which of the following ionic compounds has the largest lattice energy? The lattice energy most favorable to a stable lattice. The largest lattice energy. Remember how we determine lattice energy? We have the gas phase cation and the gas phase. Let's do it this way. I think this is the way we did it in the book. Metal and then non-metal ion. And when those come together, we get the solid MX. And that is extremely exothermic. So the most stable one is the one that has the largest release of energy, exothermic. All right, which one would that be? Well, we have to consider 2 things. Electronegativities. Negativities. And ionic size. All right, this determines the strength of the attraction. Plus, this also, we're talking about Coulomb's forces, right? The force of attraction here is equal to, let's see, some constant. And then ion 1, ion 2, divided by R. The size of the charge matters, and the distance between them also matters. So the closer they can get, the stronger the force. And the more positive, negative charges we have, the stronger the force. So a combination of those 2. All right, let's look at A, B, C, and D, and E. All right, what do we have here? Barium oxide. Right? Barium is 2+, oxygen is 2-. Beryllium oxide. Also 2+, 2-. Cesium, cesium iodide. That's a 1+ and a 1-. Sodium bromide. 1- and a plus. And barium sulfide. This is a 2- and this is a 2+. So what we can do is we can take the electronegativities. Let me squirrel another one in here. Charge size. Let's look at the charge size first, and then we can start eliminating ones. Right? We're going to eliminate the single charges. Okay. Now we've got the charge size taken care of. How about the ionic size? Right, which one is the smallest ion pair? Well, barium is huge paired with oxygen. Beryllium is really small. So these two can get a lot closer together than these two. That means we're going to choose this one over this one. Then we have to say barium and sulfur. Well, that's even worse. Sulfur is bigger than oxygen. Right? So I think we found our answer. We get the 2 plus, 2 minus, and we get the distance between them. Okay. I shouldn't have even talked about electronegativities. Why? Because these are all ionic compounds. Right. We should really only be talking about Coulomb's law. Right. And that we just need what's the size of the charges and what's the ionic size. And that gives us, these two are small enough, they get closer together, and the closer two charges get together, the stronger the force, which means they have to give up energy to get there. All right, 26. No, we haven't done 26 yet. All right, 26. We'll probably keep going until somebody shows up too. So we get all our groups together. The first electron affinity value for oxygen is blank, and the second electron affinity value is, okay, our choices: unfavorable, endothermic, favorable, exothermic. All right, electron affinities. So the first electron affinity for oxygen would be what? Oxygen, separate atom as a gas, and we got one electron, and that gives us this as a gas. So that's going to be exothermic. Right? This electron dropping into this oxygen is exothermic, which is favorable. Remember, lower energy means more stable. So when it gives up that exothermic energy, the energy of the ion is lower than the energy of the free atom. That makes it favorable. Then if we try to do the second electron affinity and give us this one, all right, is that going to be favorable or unfavorable? Try to add a negative to a negative. It's difficult. This is going to have some energy added to it. It's endothermic. Unfavorable. All right. So that one would be favorable. Unfavorable would be D. Exothermic is favorable. Endothermic is unfavorable. Right. Now, I know what you should be thinking is, yeah, but oxygen prefers a 2 minus charge, doesn't it? When it's in an ionic compound. And we know that if it picks up 2 electrons, it's going to look like neon. Right? So overall, the favorable would have to exceed the unfavorable by a significant amount for the overall to give us this ion. All right, so this one would have to be a huge exothermic advantage to counteract the smaller endothermic disadvantage. All right, that's the way I look at it. And these are measurable quantities. We're not just pulling these out of thin air. 27. Let's see, let's move it up a little bit. 27. All right. Using the following reaction data, calculate the energy of an HF bond. All right. If we want to know the energy of an HF bond, right, it needs to be in a gas. We can't have any phase change interfering with it. So this has to be a gas, and then we have to add energy to it, right? Endothermic, which means the value is going to be positive, and it gives us this separate hydrogen atom and this separate fluorine atom. Okay, that's what we're looking at. So this is our target equation. And we can use Hess's law to calculate the value of this HF. Right? This is going to be an unknown enthalpy. So what do we have to choose from? We got HF there as a gas, right? The very first one, but it's on the wrong side. Right? So if we put 2 HF on this side, and it yields H2 gas plus F2 gas, then we're going to have a change in sign, correct? 542 kilojoules. But now we got 2 of these. We only need half of them, correct? So if we take half of that one, half of this one, and half of this one, right? Then we'll take half of this one. Right, so that would be 271 kilojoules. Awesome. Okay, so that takes care of that one. All right, how about the H and the F? Well, the second one has H on the right-hand side, which is good. H2 yields 2H, that's gas, and that value is 432. But we only need half, right? There are 2 hydrogens here. We only need 1 of them. So if we divide half there and half there, right, that makes 1 there and 1 there. Then this is divided in half also. So that's 216, correct? All right. It takes care of the hydrogen. We'll do the same thing for fluorine. F2 yields 2 Fg, and that value is 154. Okay, and we're in the same situation here because we only need 1 F. So we're divide both sides, divide the whole thing by 2. Okay. So that leaves 1 here, half there, and half of this. So that's 77 kilojoules. Yep. Okay, so we've taken care of all 3 of them. And this one cancels that one, this one cancels that one. HF is covered there, H is covered here, F is covered there. So now we add them together, we get that target equation. Now we can add these together. So let's see, 7 and 7 is 14. Carry the 1, that's 8, 9, 16. And that's 1, 3, 4, 5. 564 kilojoules for that reaction. Okay. That wasn't too hard, was it? All right, 27. Let's see. Kind of wish we had finished the lab last week. Then we wouldn't have to stop. But that's all right. It's a fun lab. You've already got that part of it coming. We don't want it to go to waste. 28. As indicated by Lewis structures, which of the following would probably not exist as a stable molecule? All right. A, B, C, D, E. And our choices are, I know this one exists. That's methanol. This one is formaldehyde. This one, never seen it before. This one is acetylene. And this one, I'm not sure about that one either. What we have to do is draw Lewis dot structure to see which one is most likely. So how many electrons do we have here? That's 4. This is 3 times 1. There's a 6, and that's 1. And so that's 8, 14 electrons. This one has 6, 2 for that one, 4 for this one. So that's 12. Okay. This one would have 6 for this one, 3 for that one, 3 times 1, 4 here, so that's 13. This one has 2 for that one, and 2 times 4 is 8. So this one has 10. And this one has 4 here, and 3 times 4 is 12, so that's 16. Okay, now let's draw our structures. Carbon, the way this is an organic molecule, and the way we draw organic molecules, I may have described it before, but I'll do it again. If you see a hydrogen to the right of a carbon, all of those hydrogens belong to that carbon. And this carbon is bound to the very next atom in the list, in the row. Right? So it's actually carbon bound to oxygen. And then that other hydrogen is bound here. And these 3 hydrogens are here. Right? 2, 4, 6, 8, 10. So that means we got 4 electrons left. Can't put them on hydrogen, so we have 1, 2, 3, 4. That's an octet. These are all duets. That's an octet. That's it. So that's a reasonably stable molecule. Let's try this one. Carbon in the center. We have 2 hydrogens here. We have an oxygen on this side. That's 2, 4, 6. So 6 electrons. 1, 2, 3, 4, 5, 6. Okay. We got to make an octet for carbon. So we'll take this one and put it over here. So that means that pair becomes a bond. And that's fairly stable. I mean, that's a valid Lewis dot structure. How about CH3O? All right. So we have our carbon, we have our oxygen, we have our 3 hydrogens. 2, 4, 6, 8. Minus 8 is 5. 1, 2, 3, 4, 5. Okay, so carbon's already got an octet. Oxygen is deficient in an octet. That's probably not a good sign. Okay, the other way we can look at this is formal charge. What's the formal charge on carbon here? Well, carbon starts off at 4, right? 4 valence electrons, and 1, 2, 3, 4 minus 4. So carbon is equal to 0. How about this oxygen? Oxygen starts at 6 as a neutral atom. 1, 2, 3, 4, 5, 6 minus 6. That's equal to 0. All right. So we can't say that the formal charge is a problem. So the problem with this one is the octet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, 13. Okay, so let's keep that one. That's a possibility. C2H2. Oops. 2 carbons is 8. Oh, already got that. 8 plus 2 is 10. All right, so if we do 10, we got carbon and hydrogen. So that's 2. We got 8 more. 2, 4, 6. Wait a minute. Oh, 2 carbons. Excuse me. Flashback. I did this once before. Not yet. There we go. And then we have 2 hydrogens. 2, 4, 6. So that's 10 minus 6 is 4. 1, 2, 3, 4. All right, so how do we get an octet? 2, 4, 6. If we move this one over here and this one over here, then we get another bond. That gives us 2, 4, 6. All right, we need 2 more. Over here, over here. Triple bond. So what we get is triple bond carbon with hydrogens, and that gives us, that's everybody. Right, so this one's fairly stable. That one's good, that one's good, this one's good. How about C3H4? All right, got 16 electrons. We have 3 carbons, and these carbons are all bound to each other. We know that because hydrogens can't be in between anywhere. Right? They can only have 1 bond each. Right? So we have to put the carbons together. And then 4 hydrogens. Well, we work from the outside in. Right? There's a hydrogen. There's a hydrogen. Correct? There's a hydrogen. And there's a hydrogen. So we got 4 hydrogens, 3 carbons. Atoms are good. 16 electrons. Well, 2, 4, 6, 8, 10, 12. Minus 12. We only got 4 left. So we work from the outside in. Right? 1, 2, 3, 4. Okay. Now we have to make, excuse me, now we have to make octets for carbon. How do we do that? Well, if we take these two and put them over here, right, that'll retain the octet for this carbon and put them there. Okay, we got 6. We're not at octet yet. So if we take these other two, do like that, now we have 2, 4, 6, 8, 10, 12, 14, 16. That's the right number of electrons. So this Lewis dot structure is valid for that one. This one is questionable simply because it's missing an electron. So if we have to eliminate the best ones and keep the worst one, C seems to be the one that is least stable and indicated by Lewis structures. Okay. It's 28. Let's see, who are we waiting on? Heather.
I'm going to be closer to 2 getting there, but I will be there.
Okay, that'll give me some extra time. 29. All right. Using the following electronegativity values. Carbon is 2.5, hydrogen is 2.1, chlorine is 3.0. All right. And oxygen is 3.5. From the following group, select the molecule that fits the given statement. This molecule contains a carbon atom with trigonal planar geometry. Okay, let's see. Do we have a bunch of them? Just that one. Okay. So let's see. We've got A, B, C, D, and E is none, right? A, B, C, what D over here? All right. A, CH3CHO. CH3CHO. This is one of those molecules this is organic notation. Remember, these hydrogens belong to that carbon, and this carbon is bound to that carbon. Right, so it'll look like this. And then this hydrogen is here, and that oxygen is there. And these 3 hydrogens are here. That's the basic structure, our starting point for this molecule. All right, so how many electrons do we have to get rid of? We've got 2 carbons, right? That's 8. We've got 4 hydrogens, that's 4, and 1 oxygen, which is 6. Right? So it's 18. 18 electrons. 2, 4, 6, 8, 10, 12. Right? So we have 6 electrons left over. Yeah, I'm getting kind of messy in here. 6 electrons that we have to do. And start from the outside, work our way in. 2, 4, 6. Okay, that's not a problem, right? Because this already has an octet. This one has 6. All we have to do is make a double bond here. Okay. Double bond. And there we go. Okay, what's the geometry around this carbon? 1, 2, 3, 4 groups, and no lone pairs. It's tetrahedron. Right. This is a tetrahedron. Right. How about this one? 1, 2, 3 groups. Nobody remembers? Trigonal planar. Like BH3, like trigonal planar. Okay. Oh, we found our answer. Right. Which one has, you know what? Those electronegativities, that's blue smoke. You don't need them, not to answer that question. Okay. It's like I always say, multiple choice questions, word problems. are designed to confuse. So we read that into the court records, right? But we didn't need it. We found it, right? We know carbon dioxide is linear, right? We did that before. CH3Cl, that's tetrahedral, right? Carbon's in the center, 3 hydrogens in the chlorine. C2H6, C2H6. And that should be all of them, right? 4, 8, 9, 10, 11, 12, 13, 14 electrons. 2, 4, 6, 8, 10, 12, 13, 14. 2, 4, 6. 1, 2, 3, 4, 5, 6, 7. 7 times 2 is 14. Okay, that was good. And those are both tetrahedral. We have 4 groups around the central atom. This is a central atom and this is a central atom. I know during the lecture we talked about only very simple molecules. But now we're starting to expand, and you can have different geometries around each of several central atoms in larger molecules. So we found our answer is A. All right. Let's scoot on down to 34. Of the following, which molecule has the largest bond angle? All right. So we did ozone before. Ozone. And it looked like, well, actually it was resonant. But one of the valid Lewis structures was this one, and let's see, this one, and this one. And that, right? 2, 4, 6, 8, 10, 12, 14, 16, 18. 3 times 6 is 18. Okay, so that's good. What's this bond angle? Well, we would expect it to be 120 degrees, right? If it's trigonal planar, electronic. So we would start off at 120, but with this lone pair up here, it'd probably be less. Right, maybe 115 or something like that. Because remember what lone pairs do. Right? They're not confined by a bond, so a lone pair goes like that, and it puts pressure on all the other electrons. How about OF2? Right? 2 times 7 is 14 plus 6, that's 20 electrons. So we have oxygen in the middle, fluorine, 2, 4. 16. 2, 4, 6, 8, 10, 12. 4. There. Okay, octet, octet, octet. This is a tetrahedron. Right, as it mentioned, largest bond angle. Okay, there's only one bond angle here. So with 4 groups, you're going to have a bent molecule, right? But the bent molecule is derived from a tetrahedron. And remember what the angle for a tetrahedron is? 109.5. Now, again, it's going to be less than that because we've got 2 lone pairs up here pushing that bond down. But that's our starting point. How about C? HCN. HCN. All right, so we got 5, 4, and 1, which should be 10 electrons. We have carbon in the middle, nitrogen, hydrogen, 2, 4. That's 6 electrons. 2, 3, 4, 5, 6. All right. If we're going to make an octet for carbon, we've got to pull 2 of these over here. That one, and that one. So now we have H, C, triple bond N, like that. The central atom here is the apex of a linear molecule. Right? 2 groups means linear. So this is 180 degrees. Right? About D. Water. Water is like this one. O, hydrogen like that, like that. So that's 109.5 or something less. But the largest bond angle here is this linear molecule, 180 degrees. That's hydrogen cyanide. Everybody take a deep breath. Hope everybody's got a will. Because that stuff will kill you. All right. 35. Which of the following molecules is non-polar overall? Some of these we did already, so maybe we can fly through this pretty quick. SF4. And so that's 4 times 7 is 28, plus 6 for sulfur is 34, right? 28, 34, 28, 6, yeah, 34. So if we did this, F, 2, 4, 6, 8, that's 26. Let's see, 6 more around each of these fluorines means 24 used up, right? So we have 2. Goes here. All right. So this molecule is going to be what? If it's got 5 groups around sulfur, we're talking about trigonal bipyramid. So if we do the trigonal part here, right, and then we have the sulfur in the middle, and we've got something up here and something down here, right? Okay, we've got 4 fluorines, but we need a lone pair. Where does the lone pair go on a trigonal bipyramid? It goes on the triangle. And here, here. So we put the other 4 fluorines here, 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 and here, and we draw the bonds to each one. What do we get? Get a seesaw. Get a seesaw. And the polarity of the bonds, like this, like that, like this, like that, are not symmetrical. So we do have a polar molecule here. SF2. Okay. 2 times 7 is 14, plus 6 is 20 electrons. So we have an S, F, and an F. 2, 4. That's 16 electrons left over. 2, 4, 6, 8, 10, 12. Well, it's 4 electrons. 1, 2, 2. Okay. That's a tetrahedron around this central atom. So we've got a sulfur here, we've got fluorines there, and we've got 2 lone pairs here and here. That's like water. This is a polar molecule. C, carbon tetrachloride. All right, we have 4 times 7 is 28, plus 4 is 32. We have carbon in the middle. We have chlorine here, chlorine here, chlorine here, chlorine here, 2, 4, 6, 8. All right, so that's 24, correct? 2, 4, 6. 6 extra electrons around each one of those chlorines. 6 times 4 is 24. So all of our electrons will be used up. That's a tetrahedron. It's a polar bond here, 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 and here, but they're all symmetrically arranged in a tetrahedron. They cancel one another out. This is non-polar. Okay. So we found our answer. Right, we can move on. The other 2 are polar. And I welcome you to draw them out and satisfy yourself. But we found the answer. Carbon tetrachloride is non-polar. That's why it made such a good dry cleaning agent. Right. Years ago, back when I was a kid, they used carbon tetrachloride as a dry cleaning agent, and it was a health hazard for their workers. So Ocean EPA got together and says, all right, no more, can't use it anymore. So they had to find something else, which was more expensive, of course. What they ought to use is supercritical fluids like carbon dioxide. You know, lots of carbon dioxide. Remember what a supercritical fluid is? We haven't got to that yet. Oh, second semester, come back. 36. Which of the following molecules are non-linear? All right. We got NO2 minus, got C2H2, got N3 minus, got HCN, got CO2, and we got H2O2. Put it over here. All right. We did this one just a few minutes ago. This is acetylene. That's linear. We did this one a few minutes ago. Hydrogen cyanide. That's linear. We've done this one umpteen number of times. That's linear, right? So if we're looking for nonlinear molecules, it's got to be one of these, or many, maybe more of them. So we don't have to waste our time on those. We already know those are linear. How about this one? And so 2 electrons here, 2 times 6 is 12. So we got 14 electrons. Right? O, O, H, H, 2, 4, 6. And it's 8 electrons. 2, 3, 4, 5, 6, 7, 8. Okay. This one is going to be shaped around this one is a tetrahedron. And so we're going to have, think water, like this, and like that. Okay, for this central atom. And now we got this one. So rather than put that other hydrogen over here where it can get, we call it steric hindrance, where it can get in the way of this one, we're going to put that other hydrogen out here, like that. And these lone pair electrons like that. So that's a tetrahedron, but it's bent and bent. So this one's nonlinear. We know that was nonlinear. So H2O2 is nonlinear. Okay. How about NO2 minus? All right, nitrogen's 5. 2 times 6 is 12 for oxygen plus 1. And so that's 18 electrons. We have nitrogen, oxygen, oxygen, 2, 4, 14 electrons. 2, 4, 6, 8, 10, 12, 14. All right. So how are we going to do this? Well, we got to leave this lone pair here, because if we try to make a double bond out of it, that doesn't take us anywhere. We're trying for an octet. So if we make a double bond here with those two, that means 2, 4, 6, 8. Or we could do it resonant, like this. So these two would resonate backwards and forwards. And don't forget the negative. All right, so around this central atom, we've got, let's see. Yeah, there we go. 1, 2, 3. We got 3 groups around that central atom, which is trigonal planar, electronic. And if we cover up this one, that makes it bent. So this one is also polar. Or what does it say? Nonlinear. This one's nonlinear. Okay, either one of them works as nonlinear. And the last one, N3 minus. So we've got 3 times 5 is 15 plus 1 is 16 electrons. N, in 2, 4. That's 4. That's 12 electrons. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. We need an octet around this nitrogen. Let's see. 2, 4, 6, 8, 10, 12, 14, 16, 16. Okay, just checking. All right, so we could take 2 from here, right? Do that. Or we could take 2 from the other side. Do it like that. But actually that doesn't help the same. Right? 2, 4, 6, 8, 10, 12, 16. We're going to have to take 2 more from the other side. Like that. Right. To put an octet around that nitrogen and keep the octets here. 2, 4, 6, 8, 2, 4, 6, 8. So this one is linear. All right, so we only got 2 non-linears, H2O2 and NO2 minus. H2O2 and NO2 minus. C. Okay. All right. 36, 38. Are we expecting anybody else? Yeah, we are. Heather. Almost forgot.
Yeah, I'm pulling into the school now, so I'll be there in a minute.
Okay. Molecular structure of BRF6 plus. BRF6 plus. Bromine is less electronegative than fluorine, so it's going to be in the center. And for balance purposes also. So we've got 7 halogens. 7 times 7 is 49 minus 1. 48 electrons. Okay. So Br in the middle and 6 around it. 1, 2, 3, 4, 5, 6. Yeah. Yeah. So that's 2, 4, 6, 8, 10, 12. 36. 2, 4, 6. 6 times 6 is 36. We've used them all up. You put 6 more electrons around each one of those fluorine to make an octet, then you've got octahedron. Right? C. There you go. All right, 38, 39. 39. What type of structure does xenon oxyfluoride difluoride? Yeah. That's CO2. Okay. This is a halogen, so it's going to have 8 valence electrons. Oxygen's got 6, and 2 fluorines is 14. All right, so let's see, 28. 28 electrons. So we're going to put xenon in the center. It's the least electronegative of these groups, of this group. And there's 1 oxygen here, there's a fluorine there, and there's a fluorine there. So we got 2, 4, 6 equals 22. So start from the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18. So all these guys have octets. 18 is 4. So we have 2 more pair that we need to put in here. There we go. That's everybody. Now around that central atom, we've got what? 1, 2, 3, 4, 5. We've got 5 groups, which means electronic geometry is trigonal bipyramid. Okay, so if we draw the trigonal bipyramid like this, with the xenon in the center, then we're going to have something up here and something down here. Okay. So we got two lone pairs. Where do they go? In a trigonal bipyramid, the lone pairs go on the triangle. So we got a lone pair here and a lone pair here. So if we draw, if we got a probably got a fluorine here and a fluorine here and an oxygen there. So if we draw the bonds between the two, what we have is right angles there, 180 degrees. We have a T shape. If we draw it out like this, the molecule would look like this, and like that. 39. T shape. There we go. C. Okay. 39. And let's see. 44. All right, number 44. Select the correct molecular structure for silicon tetrahydride. All right. Silicon is in carbon's group, so it has 4 electrons. 4 times 1 is 4 here, so we only have 8 electrons that can be positioned. Silicon, hydrogen, 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 hydrogen. 2, 4, 6, 8. We used them all up. All right. 4 groups means tetrahedron. Okay, that would be B in this case. All right, scroll to the next one. 46. Correct molecular structure for beryllium dichloride. Okay. Beryllium is an alkaline earth, so it only has 2 valence electrons. Chlorine is a halogen with 7 each, so that's 2 times 7 is 14. We have 16 electrons. Okay. Beryllium, chlorine, so that's 2, 4. Right. 12 electrons left. 2, 4, 6, 8, 10, 12. All used up. Okay. So 2 groups around the central atom means linear. Okay. Takes care of 46. And we scroll to 48. I better put those separate. 48, here we go. 48. In the molecule xenon difluoride. How many pairs of electrons surround xenon, and what's the molecular geometry? Okay, so xenon has 8, and 2 times 7 is 14. That's equal to 22 electrons. Okay, so we have xenon. We have a fluorine here and a fluorine there. That's 2, 4, 18, 2, 4, 6, 8, 10, 12. That's octet, and we've used 12 more. So 6 electrons means 2 here, 2 here, and 2 here. Okay, so we have 1, 2, 3, 4, 5 groups, which is what electronic structure. The electronic structure is trigonal bipyramid. Okay, so if we try, if we do the triangle, right, and then xenon's in the middle, it's got something up here and something down here. That's 1, 2, 3, 4, 5. Right, you got 3 lone pairs. Where do they go? On the triangle. Okay, and our fluorine goes up here, and fluorine goes down there. So the molecular structure here is linear, right? We have 3 pairs of electrons, 3 lone pairs, and linear form. So C is the answer. Okay. All right, that's 48. $49. All right, here we go. 49. Choose the member of each set that best matches the label. Okay, so we got 3 sets. We want to find the more metallic out of beryllium, and barium, correct? We want the more metallic. Right. More covalent out of the next set. What do we have to choose from? We have N2O gas, N2O gas, or MgO, MgO solid. Okay. And then the last one is highest electronegativity. Yeah, highest electronegativity. Right. Out of oxygen, sulfur, and bromine. All right, so the more metallic is the one furthest to the left and furthest down, right? The more metallic, the most metallic element in the periodic table is in the lower left-hand corner. And what we mean by metallic in this context is which one is the least electronegative. The least electronegative is the more metallic one. So beryllium is up, barium is way down. This is the more metallic one, barium. The more covalent. This is a metal, non-metal. This is a non-metal, non-metal. This is going to be the more covalent. The closer their electronegativities are to each other, the more covalent they are. All right, and the highest electronegativity is in the upper right-hand corner if we can get there. So we've got bromine. Bromine is situated here. And then sulfur is up here. And oxygen is up here. So oxygen should be the most electronegative. Oxygen. Okay, so which one is that? Barium, N2O, and oxygen. Barium, N2O, and oxygen is E. Okay. Yeah, that one. And 50 coming up. Here we go. 50. So what do we want to do with 50? Use the bond energies given below to calculate the enthalpy change for the reaction. HCN gas plus 2 H2 gas yields CH3 NH2 gas. Okay. So in order to use the bond energies, we have to know what bonds are there. What bonds are in this reaction. We drew this one earlier. we know that HCN is like this and that. We know that hydrogen is like this and that. Okay. This one may be a little different. So we're going to have to draw the Lewis structure for CH3NH2. Okay. So we have 4, 3 for this one, 5 for that one, and 2 for this one. So that's 5, 10, 14. 14 electrons. All right. So remember, all these hydrogens belong to that carbon, and then it's connected to the nitrogen. And then we have a hydrogen here and a hydrogen there. So that gets all the hydrogens, 5 hydrogens, 1 nitrogen, 1 carbon, 2, 4, 6, 8, 10, 12. So we have 2 electrons left. We can't put any on the hydrogens. Carbon's already got an octet, so we have to go here. Right? Now we've used them all up. Okay, what we need is to be sure we have an octet or a duet. Right? Duet. Octet, 2, 4, 6, 8 octet. So this would be the structure, the Lewis structure for that molecule. Now we can use our formula. Right? Delta H is going to be equal to the sum of with the coefficients, the number of moles, the coefficients. This is 1, that's 2, that's 1. And we have to assume that the equation is balanced. We can check it to be sure. And the bond energies for the reactants minus the bond energies, oops, not really, bond energy for the products. Okay, so our delta H is going to be equal to, do the reactants first. We got 1 hydrogen here, hydrogen carbon. Hydrogen carbon is 413 kilojoules, and there's only 1 mole. So that's that many kilojoules. Now we've got a carbon triple bond nitrogen, which is 891 kilojoules, because there's only 1 of them, 1 mole. All right, now we subtract, oh, excuse me, I'm not done yet. We have to add 2 times hydrogen-hydrogen bond, which is 432. There we go. Now, that's the bond energy, all the total bond energies for the reactants. Now we need to subtract the products. So we've got 1, 2, 3. Yeah, we've got 3 carbon hydrogens. 3 carbon hydrogens, 413. Right? Then we're going to add 1 carbon nitrogen, 305. And these are still kilojoules. Then we've got 2 nitrogen hydrogens. 2 nitrogen hydrogen is 391. Okay? So that's the thinking part. The next thing we have to do is crunch the numbers. All right, so let's do this one first. 430, I'm gonna work backwards. 432, 2 times that, then 891 plus that, and 413 plus that. So we got 2168. 2168 kilojoules. What does that mean? That means the total of all the bond energies of the reactants. That's the total bond energy of the reactants. That's how much energy it takes to break every bond in the reactants. Now we're going to get some of that energy back, right? Because this negative makes it exothermic. This is endothermic. This makes all of those exothermic. We're going to get some of that energy back. Right? So we're going to say 3 times 413. Okay. And then 305 added to that. And then 2 times 391 and add that together. And on this side, we get 2, 3, 2, 6. And this one is subtracted from that one. So what I get is a delta H of minus 158 kilojoules. That would be B. Okay? That's how it's done. Number 50. Okay, scroll to the next one. 51. All right, this one's going to take some doing. 51. Give myself as much board room as I can. All right, given these following, the following information. Right, so we've got 1, 2, 3, 4, 5, 6 reactions written this way, and they're defined as to what they are. Then what we want to do is calculate the change, the enthalpy change for this reaction. This is our target reaction. So 2 lithium solid plus 2 HBr. What is that? That's a gas. And that yields what? H2 gas plus lithium bromide. 2 lithium bromide. Okay. This is actually Hess's law. All right, so which one has lithium solid in it? The first one does. So we'll use the first one, right? Lithium solid plus, no, yields, excuse me. Yields. I'm going to keep the yield signs in vertically here. So that one yields lithium gas. This would be the enthalpy of sublimation. We're going from a solid to a gas, right? But we need 2 of them, right? So over here, we've got our delta H, and this is our question right here, kilojoules. So for 1 mole of lithium, we have 166 kilojoules. 166 kilojoules, but we need 2 of them. So that's 332 kilojoules, and that's positive. You have to add energy to get this solid to go to a gas. Now we got 2 of these. All right, that's this one. That one covered with this one. Okay, how about HBr gas? HBr gas. The next one is HBr gas. Right? So HBr gas yields H gas and Br gas. H gas and Br gas. And the energy, this is the bond energy of HBr, the HBr bond, 363 kilojoules. Right? But how many do we need? Well, we need two of these. Right? We need two of these. And that gives us, yeah, we need two of those. So now we have two here and two here. And this is times two. All right, so that's 6, 12, 1 and 6 is 7 kilojoules. There we go. So this one now is covered with that reaction. Okay. Now we need hydrogen gas, diatomic hydrogen gas as a product. So let's see, do we have one of those? Yes. The last one, the bond energy of H2. So if we put H2 on this side, it's on the wrong side. It needs to be on that side. So H2 gas is on this side, and 2H gas is on this side, correct? The bond energy is 432 kilojoules, and we've got one of them. But we flipped the equation, so we have to change the sign. Minus 432. Okay, so now this one is covered there. Okay, last one, lithium bromide. Lithium bromide is the next to the last one. Lithium bromide solid. It's on the correct side of the equation. Lithium bromide solid. And this one is the lattice energy for lithium bromide. So we're going to have a lithium plus 1 gas, and then a bromine minus 1 gas. And that value is minus 809. Minus 809 kilojoules. But we need two of them. So we multiply this one times 2, 2, 2, and this one times 2. Let's see, did I change the sign? I did not. I didn't need to change the sign. Right. I only multiply it by 2. So this is, let's see, 18, carry 1, 16. So minus 16, 18 kilojoules. Okay, that covers this one. There. Okay. Now notice we've got this one hanging out, hanging. So we've got to get rid of these others. How do we get rid of lithium gas? Well, let's see. Lithium gas is on this side. So if we want to cancel it, we need lithium gas on this side, and the ionization energy will do that for us. So lithium gas yields lithium plus gas plus an electron. Okay, and the energy for that one is 520 kilojoules. Right? It's a plus, and that's a plus. But what? We need two of them. So if we multiply 2, 2, and 2, we have to multiply this one by 2, and that's equal to 1,040 kilojoules. All right, what does that do for us? That takes out this one here. It takes out this one here, like that. Now we need bromine. So bromine's on that side. We need electron affinity to keep bromine over here and cancel that bromine. And so bromine gas plus an electron yields bromine minus 1 gas. And that will be the electron affinity minus 325 kilojoules. But we need two of them, right? One bromine here, two bromines there. So we need two, two, two. And 2 times this would be 600 minus 650 kilojoules. All right, so what does that do for us? That gets rid of this here. It takes out 2 Br minuses here. Okay. And it takes out 2 electrons here. Okay, what do we got left? These are canceled, these are canceled. We don't want to cancel that one with that one. 2 hydrogens. Oh, here we go. 2 hydrogens, 2 hydrogens. Now let's see if we're covered. These are in the target equation here, 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 right? That one's not left, not left. Cancel, 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 cancel. Okay, we got nothing hanging loose. So now we can add these values and find out what the delta H for that reaction is. All right, so let's do it. 332, add 726, subtract 432, subtract 1618, add 1040, and subtract 650. So I get minus 602. Minus 602 kilojoules is B. Okay. Now, there's another problem in here. I'm not sure if it's highlighted. Let me see. Yep, it's highlighted here. The reason I did 51 first is because these descriptive terms are included, whereas down here, they're abbreviated. And number 52, calculate the lattice energy for rubidium chloride from the following data. All right. We need to know what those abbreviations mean before we can use Hess's law to determine the lattice energy. Right. We can write the lattice energy for rubidium chloride. Right. All we need is to remember that lattice energy is built upon this equation. Rubidium plus gas plus chloride minus gas yields rubidium chloride solid. Right. That's our target equation. All right. These other equations, the first one, rubidium solid, I'm going to write them over here. Rubidium solid to rubidium gas is sublimation. And its delta H is 85.8. 0.8. And this is kilojoules. Okay. The second one is ionization energy, first ionization energy of rubidium. So we take rubidium gas, add energy to it, and we get rubidium plus gas plus electron. And that value is 397.5 kilojoules. Right? The next one is bond energy for dichlorine. So we have Cl2 gas yields 2Cl gas, and that energy is 226 kilojoules. All right. The next one is heat of formation. Right. What's the heat of formation? Remember how we write the heat of formation? We start with a product. Rubidium chloride in its most stable form, which would be a solid. right? Then we work backwards. We need rubidium in its most stable form, solid, plus chloride in its most stable form, gas, as the dichlorine, but we only need one of them. Okay? And this heat, let's see, that one, that one, that one. And then minus 431 kilojoules. Okay? And the last one is electron affinity. So electron affinity for chlorine gas, monatomic, add an electron, we get Cl minus gas, and the value for that is minus 332 kilojoules. Okay, now we can take this information and use Hess's law, right? Where do we have rubidium plus gas? Right here. But it needs to be on the other side. So if we put this one, rubidium plus gas on this side with its electron, and then rubidium atomic gas, then the value is going to be the inverse of that. The inverse of this one. 397.5 minus 397.5 kilojoules. Okay, so that gives us this one covered right here, here, and here. Okay, now how about the chloride? Well, let's see. Here's the chloride. It needs to be on this side. So if we put the chloride here, and we have chlorine, atomic chlorine, plus its electron, then instead of minus 332, it's going to be a plus 332 kilojoules. Okay, that takes care of this one here. All right, now we have rubidium chloride solid. Let's see, rubidium chloride solid. Here it is. Okay. It needs to be on that side. So we'll put it on this side where that equation says it is. Rubidium chloride solid. And on this side, we have rubidium solid plus 1/2 chlorine gas. That takes care of this one. And we can use this value as is, minus 431. Okay. Now what we have to do, and we've used, let's see, let me mark off the ones we've used. This one. We've used this one. We've used this one. Okay. And we've used this one. All right. So we need rubidium solid on that side. Here's rubidium solid. So let's put rubidium solid on this side so it will cancel. And then this has to be rubidium gas on that side. And we flip the equation. So the value is minus 85.8 kilojoules. All right, what does that do for us? This rubidium gas is canceled here. And these electrons are canceled also. Might as well get rid of those. Okay. And this rubidium solid here cancels that rubidium solid. Okay, so what do we got left? Well, we've got chlorine gas on this side. We got 1/2 of chlorine on this side. And that looks like this one. That's the only thing that we have left. We've used this one. And here. So how about this one? Well, if we've got chlorine on that side and half a chlorine on this side, that cancels this half of chlorine and leaves a half of chlorine on that side. So we need another half of chlorine on this side. Right? So, let's see, we got this one, that one. Okay. Yeah. We need this atomic chlorine over here on this side. Right? It's on the wrong side. It needs to be on this side. So if we put 2 atomic chlorine gas yields Cl2 gas, then what we've done is we've flipped the equation. And now instead of plus 226, it's minus 226. Okay. But we only need one of these and a half of that one. So if we took 1/2 of the whole equation, now this one becomes 1, and this one becomes a half. And this one must be 1/2. So it's minus 113 kilojoules. Now, does that get us what we want? That one cancels this one, and this is only 1 chlorine. There's another chlorine. Now we're good. Now we can add. And this should give us the lattice energy for rubidium chloride. $332 plus 431 minus 85.8 minus and 113 minus. So this is minus 600. Let's see, delta H minus 695.3 kilojoules. See, what do we have choices? 695 rounded off. All right, so that's C. Okay. That one took a while. And to be very, very methodical about it. All right. $52. What's next? 53. Okay. Let's read the question. In spite of larger electronegativity differences between bonded atoms, beryllium in beryllium chloride, this beryllium chloride has no dipole, while sulfur dichloride does. All right, explain why. Well, let's see, we've got a comparison of beryllium chloride and sulfur dichloride. Okay. So remember what we need to know. We need to know, do they have polar bonds? And then what's the geometry? So beryllium chloride is definitely polar. It's ionic. Sulfur is far enough away from chlorine. It's just barely next to chlorine, right? So the difference is not much. But it's said that sulfur dichloride does have a dipole, All right, so we got to figure that out. Let's do the Lewis dot structure and figure out what the geometry is for this molecule using the VSEPR model. So beryllium is going to be 2 electrons, and this is 2 times 7 is 14, so we have 16 electrons. All right, beryllium, chlorine, 2, 4 minus 4 equals 12. 2, 4, 6, 8, 10, 12. Right. This is one of those cases. All right. The temptation here is to make a double bond here and a double bond here. Right. Can we do that with beryllium? Right. Beryllium is 4 electrons, so it has 1s2, 2s2. Right. Where are you going to put those extra electrons? Well, supposedly we have access to p's. So we could put 2 more electrons here and 2 more electrons there. All right, so we could do that. But it's not going to change the answer, right? If we did that here and here, like that, we would still have 2 groups, and this would be a linear molecule, right? With a bond polarity that way and a bond polarity this way, both equal and opposite, equal in magnitude, opposite in direction. They cancel one another out. This is non-polar. Why? Because the molecule is linear and symmetrical, so that the 2 polar bonds cancel one another out. Okay, how about this one? Well, let's see, sulfur is in the oxygen group, it has 6, and then 2 times 7 is 14, so we have 20 electrons here. We have a sulfur in the middle, we have a chlorine and a chlorine, so that's 2, 4, 16 electrons, 2, 4, 6, 8, 10, 12, minus 12. We have 4 electrons that have to be placed here and here. All right, so what is and they've all got octets. So what's the structure here? 1, 2, 3, 4. It's tetrahedral electronic structure. Right? So if we put sulfur in the middle, and we said, okay, we're going to have let's see, do this. There, put sulfur in the middle, and then we're going to have something up here. So we can have a pair back there, a pair back here. We can have sulfur here. Excuse me. We have chlorine here and chlorine there. Okay. So this bond then, while it's polar in this direction and polar in this direction, if we rotate it around, then we have sulfur here, chlorine there, and then we have these 2 in the back. What we have is polar bonds this way and this way, and it has a net polarity because it's asymmetrical. Now, I'm not sure if it's this way or it's this way because of those lone pairs, but the fact that it's not symmetrical, the geometry is bent, that means that you do have a net vector addition of the polarities that gives you a polar bond, a polar molecule. So this one's polar. Now you just have to put that in your own words. All right. How about this one? 54. Okay. All right. 54. ICl4 minus. ICl4 minus is the molecule. And we want the Lewis structure, we want the shape of the molecule, and the polarity of the molecule. All right. So We got 4 5 halogens equals 35 plus 1 for that one is 36 electrons. Okay, with iodine in the middle and 4 chlorine, 2, 4, 6, 8. That's 28 electrons. 2, 4, 6. 2, 4, 6. 2, 4, 6. 2, 4, 6. So it's 6 times 4 is 24. It's 4 electrons. So we had 2 here, 2 there. Okay. Now, we've got how many groups around iodine? We have 6 groups, which means octahedral. Octahedral electronic geometry. Okay, so let's try an octahedral. Means that you've got a square in the middle. You've got iodine in here, and you got something up there and something down here. Now we've got 2 lone pairs. Where do they go? In an octahedron, unlike the trigonal bipyramid, in an octahedron, the lone pairs go on the apexes. Right here, right here, here, and here. So these are occupied by chlorine. Right? Those are the bonds. Okay. So the Lewis structure would be this, only you need that negative. And since we're looking for the Lewis structure, you can put these 2 right here, but it's in a square with the 2 lone pairs here. And it needs a negative charge. Otherwise, you will not have that total amount. Right? It won't balance. So there's your Lewis dot structure, including all the lone pairs. Okay, next we want the shape of the molecule. Well, since these are lone pairs covered up, what you have is square planar. Okay, that's the shape of the molecule. Now, is it polar or non-polar? Well, chlorine is more electronegative than iodine, so it's going to have polar bonds running that direction, and that direction, and that direction. But they're all pointing to the corners of a square, which means they're symmetrical and they cancel one another out. So this molecule is non-polar. All right. And I think that's it. That's it. Okay, we're done with our review. Exam will be 2 days from now on a Thursday.